The term oxymercuration demercuration indicates that there is a mercury-based reagent involved in this reaction, which is HgOAc twice, which is mercuric acetate. So mercuric acetate is added across the double bond of the alkene and it gets removed eventually. So we don't see any mercuric acetate in our product. When we compare the starting alkene and the product, we can see an extra hydroxyl group and a hydrogen atom in the product. So in this reaction, we are adding a hydroxyl group and hydrogen atom across the double bonds. So when we compare this reaction to the hydration reaction, there is no rearrangement. That's the beauty of this reaction. So we don't get any products from the rearrangement of the carbocation. So this reaction follows Markovnikov's rule. So this Markovnikov's rule helps us to determine which side we should add the hydrogen atom and which side we should add the hydroxyl group. Based on the Markovnikov's rule, always the hydrogen atom goes to the carbon atom which contains more number of hydrogen atoms. So when you compare this side to this side contains the second side. This side contains more number of hydrogen atoms. So this side contains one hydrogen atom and we don't have any hydrogen atoms on this side. So what we do in this reaction is that we will break the double bond and we will add a hydrogen atom here and we will add a hydroxyl group here to get the product. So let's see what happens in this reaction. So in this reaction, first we are adding this mercuric acetate across the double bond. So mercuric acetate is going to look something like this. And we use the pi bond to attack here and we will break this one and this one will attack back. So that's how we form this three-membered ring with the mercury. So next what we do is that we will make use of our nucleophile. So in this reaction our nucleophile is H2O. So we can add we can add the nucleophile either from this side or from this side. But we are going to always add the nucleophile on this carbon atom to open up the ring. The reason is Markovnikov's rule. So based on the Markovnikov's rule, always the nucleophile goes to the side which contains least number of hydrogen atoms. So that's why we are opening up the three-membered ring from that side. So that's how you get the hydroxyl group on this carbon. Then you have mercuric acetate here. So as a second reagent, we are using sodium borohydride here, correct? So this sodium borohydride breaks the bond between the carbon atom and mercuric acetate. And this sodium borohydride also acts as a source of H- and it gets added here. So that's how you get this product. So in this product, we are forming a chiral center, right? So what's going to be the stereochemistry of our product? So in this reaction, we will get a racemic mixture. So how do we get a racemic mixture? So this is because of this step. So we have a nucleophile, right? And this nucleophile can attack either from this side or from this side, right? So since there is no selectivity for that attack, we will end up with a racemic product. So if we need to show the stereochemistry, so we can show it like this. The only difference between alkoxymercuration demercuration and oxymercuration demercuration of the alkene is that instead of using water as the nucleophile, here we will be using an alcohol as the nucleophile. So wherever we were adding the hydroxyl group, instead of that, we will be adding the OR part. For example, here we are using methanol as the reagent. So we will be adding OMe instead of the OH. So if we were using ethanol instead of the methanol, we will be adding the ethoxy group, that is OET instead of the OMe here. So that's the only difference between oxymercuration demercuration and alkoxymercuration demercuration. This reaction also follows the Markovnikov's rule when we determine which side we should be adding the hydrogen atom and which side we should be adding the OET or OMe. Now I want you to predict the product from these two reactions. So let's see how can we get this product from this starting material. So let's look at our reagents first. So we have mercuric acetate. So we don't find mercuric acetate anywhere in the product. We learned that one. So our next reagent is THF water mixture. So water will give us hydroxyl group. So our next reagent is sodium borohydride, which will give us a hydrogen atom, which will transfer a hydride. So that's the source of the hydrogen atom. So what we will do is that we will break this double bond and we will add hydrogen atom at one side and the hydroxyl group on the another side. So how do we determine which side we should be adding the hydrogen atom? So there comes the importance of Markovnikov's rule. Markovnikov's rule tells us that we will be adding hydrogen atom to the side at which we have most number of hydrogen atoms. So let's look at both the this carbon atom and this carbon atom to determine which side has most number of hydrogen atoms. So this carbon atom contains one more hydrogen atom. So this side we don't have any hydrogen atoms. So according to the Markovnikov's rule, we will be adding the hydrogen atom to this side and hydroxyl group to this side. So we'll be adding OH here and hydrogen atom here. So that's how we get this product. So let's see how to determine the product from this reaction. So we have mercuric acetate, which doesn't show up in our product. Then we have THF ETOH, which is ethanol. So this one will give us OET, which is the ethoxy group, and sodium borohydride is a source of hydride, which will give us our hydrogen atom. So as usual, we will break this double bond. Then we need to determine which side we should be adding the hydrogen atom and which side we should be adding the ethoxy group. So this is based on the Markovnikov's rule. So according to the Markovnikov's rule, we will be adding hydrogen atom to the side at which we have the most number of hydrogen atoms. So this side we have one hydrogen atom and this side we don't have any hydrogen atom. So we don't have any hydrogen atom there. So we will be adding our hydrogen atom here and ethoxy group to this side of the alkene.